Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen that how to find the electric field due to the line charge. And in that, we have also seen the different cases. For example, we have seen that whenever the observation point is very far away from the line charge, in that case, this line charge can be considered as the point charge. And then after, we have also seen that how to find the expression of the electric field intensity whenever the observation point is along the same axis of the line charge. So similarly, in this video let us see when the same line charge is given in the form of the circular loop, then in that case, how to find the electric field intensity at the specific location. So here, once again let us assume that we have the uniform charge density, and let's say the charge density of this circular loop is equal to lambda L. And let us also assume that this circular loop is located on the z is equal to 0 plane. That means this loop is located on the xy plane. And let's say the radius of this loop is equal to a. And let's say for this given circular loop of charge, we want to find the electric field intensity at this location. So here our observation point is located on the z-axis. So here if you once again observe, then due to the axial symmetry, for finding the expression of this electric field intensity, we will use the cylindrical coordinate systems. Alright, so as we have seen earlier, for this circular loop of charge, the total charge that is residing on the loop can be found using the line integral. That means the total charge on this loop can be given as this line integral of this lambda L times dl, where this dl represents the differential length along this loop. And as we have seen in the previous video, the electric field intensity at the specific location can be found using the following expression. So basically, here what we will do, we will take the differential length dl on the circular loop, and due to this differential length, we will find the electric field intensity at our observation point. So that will give us the electric field intensity dE. And now, if we integrate it over the entire loop, then we will find the total electric field due to this circular loop. So to find that, first of all we need the value of the dl as well as the r, where the r represents the distance between our dl and the observation point. So to find that, first of all let us define the coordinates of our source as well as the observation point. So let's say this differential length dl is located at the rho dash, phi dash and the z dash location, and likewise our observation point is located at the rho, phi and the z coordinate. So here, since the loop is located on the z is equal to 0 plane, so we can say that over here this z dash is equal to 0. Moreover, at our chosen point, this phi dash is also equal to 0. And here we can say that this rho dash is equal to a. That means here these coordinates are a0, 0. Likewise, if we see the coordinates of our observation point, then they are 0, 0, z. Because if you see this observation point, then it is located on the z-axis. So therefore, this rho will be equal to 0. And since it is located on the z-axis, so this phi component will also become 0. So we can say that the coordinates of our observation point is 0, 0, z. So now, since we know the coordinates, so we can easily find the value of this r. So here, let's say from the origin, the position vector towards the differential length dl is equal to r1. And likewise, the position vector towards our observation point is equal to r2. So we can say that the vector r towards our observation point is equal to this r2 minus r1. That means here this r is equal to r2 minus r1. So here if you see, then r2 is nothing but z times az. And likewise this r1 is equal to this rho dash times a rho. And here since the rho dash is equal to a, so we can say that this r1 is equal to this a times a rho. That means the vector r is equal to z times az minus a times a rho. And if we see its magnitude, then that is equal to square root of z square plus a square. So in this way, we got the value of the R. So now the only thing that we need is the value of the dl. So here if you see this dl, then it represents the arc. And in the cylindrical coordinate system, this dl can be given as this rho dash times d phi dash. So here this rho dash is nothing but the a. So we can say that here the dl is equal to a times d phi dash. So now let us try to put all these values in the above expression and let us try to simplify it. But before that, this expression can be further written as integration of lambda L times dl divided by 4 pi times epsilon naught times r square times r divided by the magnitude of the r. That means here in the denominator we will have the r cube. So in this expression, now we can put the value of the dl as well as the r. So if we put all these values, then this is the expression of the electric field intensity. So here if you see, then this electric field intensity consists of the two components. One is the Ez and the second one is the E rho. So here, if you see this Ez component, then it will point in this direction. While if you see the E rho component, then it will point radially outwards. That means here, this is the Ez component and this is the E rho component. That means during our integration, whenever we take the differential length dl, then for the each differential length dl, we will get these two components. And at each location, the Ez component will point in this direction and the E rho component will point radially outwards. So here, if you closely observe, then due to the axial symmetry of the ring, the E rho component will get cancelled out. For example, whenever the differential length dl is located at the phi is equal to 0 point, then this E rho component will point in this direction. And similarly, whenever we are finding the electric field intensity due to the dl component which is located at the phi is equal to pi or at this location, then at that point, this E phi component will point in this direction. That means the E rho component at phi is equal to 0 and the E rho component at phi is equal to pi will cancel out each other, and the same thing will happen at every point. So due to that, in the final expression, we will not have the E rho component, and therefore this component will get cancelled out, and effectively we will only have the Ez component. So we can say that now this electric field intensity is equal to integration of this lambda L times dl divided by this 4 pi times epsilon naught times this z square plus a square raised to 3 by 2. And here, as we have seen, this dl is equal to a times d phi dash. So we can say that this is equal to lambda L times a times d phi dash divided by this 4 pi epsilon naught times this z square plus a square raised to 3 by 2. And of course, here we will also have this z times az. And as we have seen, this component will get cancelled out. So we can say that this is equal to Ez is equal to integration of lambda L times a times d phi dash divided by 4 pi times epsilon naught times z square plus a square raised to 3 by 2 times z. So of course, here we will also have the unit vector az, but since we are explicitly writing the Ez, so there is no need to write the az. And here the limits will be from 0 to 2 pi, because here during our integration we are integrating from phi is equal to 0 to phi is equal to 2 pi. That means here, except the d phi dash, all the components are constant. And we know that if we integrate the d phi dash over the given limits, then we will get the 2 pi. That means the overall expression will be equal to this lambda L times 2 pi times a times z divided by these 4 pi times epsilon naught times these z square plus a square raised to 3 by 2. So now here if you observe, then this 2 pi a times lambda L is nothing but the overall charge of this circular loop, because we know that for the circular loop, whenever we have the uniform charge density, then the total charge Q can be given as this lambda L times the circumference of this loop, that is equal to 2 pi times A. So here we can say that this expression is equal to q times z divided by 4 pi times epsilon naught times z square plus a square raised to 3 by 2, where this q represents the total charge of this circular loop. So in this way, we got the expression of the electric field intensity for this circular loop. That means this is the expression of the electric field intensity at our observation point due to the circular loop of charge. So now, for the circular loop of charge, let us see some special cases and let us find out for such cases how to find the electric field intensity. So one of the cases when this observation point is located at the center of this ring. So in that case if you see, then for that case the z will become 0, because now our observation point is also located on the z is equal to 0 plane. So in that case if you see, then in this expression the z will become 0, and in that case this E will also become 0. So from this we can say that the electric field intensity at the center of the circular loop of charge will be equal to 0. Similarly, the other extreme case is whenever this observation point is much farther away from the circular loop. So we can say that this z is much greater than the a. So in this case if you see, then this a is negligible compared to the z. So in that case, the expression of the E can be written as this q times z divided by these 4 pi times epsilon naught times these z square raised to 3 by 2, because here this a is negligible, and therefore further this expression can be written as this q divided by this 4 pi times epsilon naught times z square, where the z represents the distance between the observation point and the circular loop. So as you can see, whenever our observation point is very far away from the circular loop, then in that case this circular loop can be considered as the point charge, and in that case the expression of the electric field is similar to the point charge expression. So in this way, if we have been given the circular loop of charge, then also we can easily find the electric field intensity. So similarly, in the next video, we will find the electric field intensity due to the surface charge. But I hope in this video you understood how to find the electric field intensity whenever we have the circular loop of charge. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.